Now that we have a conceptual understanding of what entropy is, we're going to come up with a quantitative description or a quantitative definition for a change in entropy to a system. And for that purpose, we're going to use a reversible process. And that's just a process that's capable of achieving equilibrium. If you change the conditions just a little bit, the reaction will go forward or in reverse. And a phase change is a pretty handy example to use to create that definition. Essentially, we're just going to boil some water. If we add just a little bit of heat to a pot of water to move it from the liquid phase into the vapor phase, we know we're going to get an increase in entropy because the vapor phase has so much more entropy than the liquid phase. So we can come up with our definition for this system as the change in entropy for our system is going to equal Q, and Q is just the amount of heat that we're adding to our system in this case, divided by the absolute temperature. And phase changes do happen at constant temperature. In the case of water, water boils at 373 Kelvin or 100 degrees Celsius. So here is our definition for the change in entropy to our system. It's just delta S is equal to Q over T. Q is in joules, which is symbol is J, and Kelvin over here is in Kelvin. So our units for our change in entropy will be joules per Kelvin. Now, I think you can see that if we're adding heat to the system, that's endothermic. That's going to produce for our system a positive change in entropy. So that would be Q positive divided by temperature. And if we removed a little bit of heat from the system, so that the system went from a gas phase back to the liquid phase, we would have a negative change in entropy because we're just removing a little bit of heat from the system. There's one other thing that I want you to remember from Chem 1. When we looked at Q with respect to specific heat that we were talking about back in thermodynamics, that's chapter 5. If Q is at constant pressure, then Q is equal to the delta H of this process or of a reaction. So if Q is at constant pressure, then Q is equal to delta H. There's one other thing that we want to look at with respect to our new definition. If we look at the delta S as being equal to Q divided by temperature, and we're looking at the change in entropy. If this temperature, this constant temperature, is already very low, let's say 4 kelvins, so that's a very low temperature. If the system is already at a 4 Kelvin, then any heat that we add to the system will produce a significant change in the entropy of the system. On the other hand, if the system is already at a high temperature, it is so already maxed out in its entropy that if we add heat, that heat just sort of disappears into that highly disordered system, and so it's not going to be significant if we add heat to a system that's at high temperature. So if we have a high temperature, any additions of heat, not significant. If we have a low temperature, any additions of heat will be significant. Now that I have a definition for the change in entropy for a system, let's use it to do a simple calculation. During the phase change, an enthalpy change occurs at a constant temperature, and that's just going to be the amount of heat that's either released by the system if it's an exothermic process or added to the system if it's an endothermic process. All we have to do is figure out which sign we have. So water vaporizes at 100 degrees Celsius. That is, it boils at 100 degrees Celsius. And if we're boiling water, we're adding heat to the system. So the delta H of vaporization is a positive value, and that's going to be in kilojoules per mole. On the other hand, our problem says, calculate the entropy change when 1 mole of water condenses. Well, now we're going the other way. Water is condensing, and so it's losing heat in order to convert from the gas phase to the liquid phase. So the delta H of condensation is going to be a minus 40.67 kilojoules per mole. So let's use our definition under conditions of constant pressure where delta H can be substituted for Q, and let's calculate the joules per Kelvin. That is the change in entropy for our system, and we'll do it in dimensional analysis style. So this is just actually going to be delta S for our system, which is just going to be in X joules per Kelvin. So I have 1.00 moles of water. I need to go ahead, substitute my delta H of condensation, which is going to be minus 40.67 kilojoules per 1 mole of water. And then since my units on entropy are joules per Kelvin, I need to convert kilojoules to joules, and every 1 kilojoule is equal to 1,000 joules. Now, if I do this calculation, moles cancels, kilojoules cancels, and I'm left with joules. But that's only part of my answer. My answer also needs Kelvin. I need to divide by the absolute temperature at which this phase change is occurring, which is 373 kelvins. And when I do that, I come out with a value of minus 109 joules per Kelvin for my change in entropy for the condensation of 1 mole of water. Now I want to introduce you to standard molar entropies. And we can't talk about standard molar entropies unless we introduce you to the third law of thermodynamics, and I promise this is the last law of thermodynamics that I'm going to introduce you to. So according to the third law of thermodynamics, the entropy of a pure, perfect crystal at 0 Kelvin is 0 entropy. Now, I don't know about you, but I haven't seen too many pure, perfect crystals, and I certainly haven't seen any pure and perfect crystals that are at 0 Kelvin, which is a theoretically low temperature. Human beings, scientists, have gotten very close to 0 Kelvin, but it's not 0 Kelvin. And that's going to be a very unusual phase of matter called a Bose-Einstein condensate, which I know nothing about, so I'm not really qualified to talk about it anyway. So let's take a look at our pure and perfect crystal. Perfect symmetry, very, very simple, and it's at 0 Kelvin, which means the particles aren't moving at all. And so they actually have this theoretical value, 0 Kelvin. It's pure, it's perfect, and so the entropy is 0. 0 entropy for our pure and perfect crystal. Let's think about this just a little bit. If nothing that exists is at 0 Kelvin and hardly pure and perfect in the terms of having 0 disorder, then everything has disorder of some kind if it exists, which means that everything has a positive entropy. And that includes elements in their standard states, in their elemental form, positive entropy for literally everything. And if we have a positive entropy for literally everything, and we examine those substances under a specific set of standard conditions, we can come up with what we call the standard molar value for entropy. And you remember that little 0 up here. What does it stand for? It stands for standard conditions. Standard conditions for that little 0 that we always put up there next to those values, and you usually find those values in tables. And our standard conditions for entropy are 1 atmosphere, the standard state, if it's a gas, and a 1 molar concentration if it's in solution. So once again, standard molar entropies represent the amount of energy that has to be dispersed for any given substance to come into existence. Standard molar entropy is always positive because there's nothing that is either pure, perfect symmetry, and at 0 Kelvin. I know you might think you're perfect, and many of you are very close, but Trust me, nobody's perfect. Just wait till you get married. You'll find out. And we can look up those standard molar entropies in Appendix B of the textbook or some appendix in any textbook, and they're at 25 degrees Celsius. You always specify the temperature. So 298 Kelvin is the standard temperature. And you can see that for gases, our standard molar entropies are quite high. And notice all the standard molar entropies, they're positive values because anything that exists has a positive standard molar entropy. Gases have very high entropy, liquids not so bad, and then solids much lower entropies because they are much more ordered substances. They're not moving around too much, and they occupy a fixed amount of volume. We can calculate entropy change for a process or a reaction using those standard molar entropies in the same way you calculated the delta H for a reaction under standard conditions using the delta H of formation. And generally standard molar entropies and the delta H of formation will be in the same set of tables, so you'll see both of those values right next to each other. And it's calculated the same way. The change in entropy for a reaction under standard conditions, there ought to be a little zero up here, is equal to the sum of the product standard molar entropies, and N stands for the coefficients from the balanced chemical reaction minus the sum of the reactant standard molar entropies. So it's always products minus reactants. So now let's go ahead and use the tables of standard molar entropies to do a simple calculation for a chemical reaction. And by the way, before we start, what would you predict from this reaction? Would you predict delta S of this reaction would be positive or negative? You can usually make that determination of whether it will be positive or negative by simply looking at the phases and how many moles of what phase you have going from reactants to products. But let's go ahead and do our calculation of the change in entropy under standard conditions, which is just going to be products minus reactants. Okay, so here we go. So if I'm looking at my first product, it's carbon dioxide, but there are 3 of them. And remember, the standard molar entropy is in joules per mole Kelvin. So it's 213.7 joules per 1 mole. So I need to go ahead and multiply my 213.7 by 3 plus 4 moles of my other product, water, in the liquid phase. And by the way, make sure that when you look these values up, that you pay attention to what the phases are. If you miss the phase, different phases have different standard molar entropies. So this is liquid water, and so that's going to be 4 times 69.9. I'm going to close off that, minus my reactants, which will be, and there is 1 mole of propane over here, 269.9, plus, I have 5 waters, so that's going to be 5 times 205.0. And when I add all of that up, I come up with a delta S under standard conditions that's equal to a minus 374.2 joules per Kelvin.